Well, thank you all for being here. Good afternoon, first of all. And you can give yourself some applause because you have been through this conference all throughout, and now it is the final day. So give yourself some applause already. Thank you. Um, okay, we're going to talk about continuations, the magic behind virtual threads. Now, virtual threads, as we know, is an important feature of Project Loom. It is also a final feature since Java 21. And it promises to bring this high scalability benefit to Java. But the real hero of the story is continuations. Continuations is actually the magic that enables virtual threads to provide this high scalability. And that is exactly what we're going to explore in this talk. So before we get there, I just want to take a quick quick view of this room. So please raise your hand if you are using Java 21 in any of your applications. Even if it's one application, even if it's just a dummy example application, please raise your hand. Okay, I don't see that many hands. Maybe this is like 10% of the room. Come on, we could do better. But people who raise their hands have the possibility to use virtual threads in your applications. So now keep your hand raised, or again raise your hand if you're using virtual threads. Oh, okay, that's 5% or maybe even less. That's too less. I think we can do better. We can do better. Okay. So what we'll do in this talk, I hope this will help you and motivate you to then start experimenting with virtual threads and then start using them, and then we would have the next time more hands raised. So what we will do in this talk is actually the whole thing is divided into 3 parts. In part 1, we will get a very quick introduction to virtual threads. In part 2, we will explore what continuations are. What are they, how do they work in Java, and what can be they used for? And in part 3, we will actually use our understanding of continuations to create a simple version of virtual thread. So we will write our own virtual thread, and we will see if that provides these high scalability benefits. So that is going to be the flow of this talk. So let's get started. But before, a very quick intro about me. My name is Balkrishna Rahul, and I work for ING Bank. Okay, let's start with part 1, which is introduction to virtual threads. So what we see here in this picture is we have an instance of JVM, which is running on some operating system. And the JVM has a bunch of virtual threads. It also has few platform threads. And the operating system has some OS threads. Let's start with the platform threads first. Now, platform threads are the threads that platform threads are the threads that are a thin wrapper over your operating system. Now, what that means is when JVM wants to create a new platform thread, it actually requests operating system to create a new OS thread. And only when that OS thread can be created, it creates this platform thread instance. And because of that, these platform threads map to this operating system thread with this one-to-one mapping. What that means is you have one platform thread connected to exactly one OS thread. Also, creating a platform thread is a resource-intensive task. Right? When you are done with a platform thread, you don't throw it away, because creating them often is going to put a lot of load on your system. So you don't want to throw it away. You put it in a pool. And therefore, thread pools are essential when it comes to platform threads. So when you're done with the thread, you don't throw it away, put it in a pool. Next time when you need it, you get it from the pool. Right? That's the thing how you use platform threads. Now, virtual threads, on the other hand, are lightweight user threads. Lightweight, meaning they require significantly less memory. And because of that, you can create them in abundance. You can create thousands or even millions of virtual threads, and that makes them highly scalable. There's actually one more thing that makes them scalable, and we will see that on the next slide. But before that, let's see that using virtual threads in a thread pool is sort of anti-pattern, because creating a virtual thread is a cheap operation. You can create them as many as you want. Now, when you're done with it, you can throw it away, and then the next time when you need it, you can create a new one. So we don't use thread pools with virtual threads. In fact, pooling virtual threads is an anti-pattern. You don't want to do that. Okay, what we see here in this picture is we see some virtual threads which are connected to platform threads. Now, why is that? That is because a virtual thread on its own cannot execute anything. It really requires platform thread. But we also see some virtual threads which are not connected to platform threads. What about those? When do they get the platform thread? Well, for that we have virtual thread scheduler. Now, this is a newly introduced scheduler along with virtual threads. And what it does is it mounts a virtual thread onto a platform thread when a virtual thread requires platform thread. and it unmounts it when a virtual thread does not require platform thread. Now, what would be the scenarios where a virtual thread would not require platform thread? It would be when a virtual thread is waiting for something, right? And then it doesn't need to process anything, so it doesn't require platform thread. And then in that case, it gets unmounted. Now, these waiting could be waiting for a network resource to be available or waiting for a database to return something. And all of these waiting times, virtual thread does not require platform thread, so it gets unmounted. And it also relieves the CPU from any processing. Now, if you have, or if you look at a typical IO-bound application, threads spend a lot of time waiting, right? And if you use virtual threads, all of that waiting can be avoided. Meaning only your virtual threads would be waiting, but your platform threads would not be waiting, and your CPU would not be wasted, right? So if you use virtual threads, in a typical IO-bound application, CPU is highly efficiently utilized. And therefore, that makes virtual threads highly scalable. So this is actually an important reason why virtual threads are highly scalable. We'll see that with some examples also later on. One more thing about this slide, these platform threads are carrying virtual threads in this whole endeavor of mounting and unmounting. Therefore, they are also known as carrier threads. Okay, that's a lot of theory. Now let's see some action. Let's create some threads. And I'm going to switch to Eclipse. I hope the font is big enough. You can read all the way in the back. Yeah? OK, perfect. Now, let me create a platform thread first. And with Project Loom, there is a new API to create a platform thread, and that is thread.ofPlatform. And if you call this, it gives you a platform thread builder. And onto that platform thread builder, you can call start, which will start a new platform thread. And what I want to do here is I want to just print the currently executing thread. So this would be the current platform thread which is executing this line. So if I run this, then I will see that a new platform thread is getting created. Now, if there is an off-platform method, you can imagine an off-virtual method, which will give us a virtual thread. And indeed, there is. So we can do off-virtual here, and this will start a new virtual thread. So if I now run this, this will give us a new virtual thread. So this is the two-string representation of a virtual thread. And there are a couple of things to notice here. One is this part, and this is called the ID of the virtual thread, and this is unique for each virtual thread. Also, this part, everything that is after this @ mark, this is actually the platform thread onto which this virtual thread was mounted while it executed this statement. So you also get some information about the carrier thread that is carrying virtual thread if you do toString on the virtual thread that you have. Okay, there's also a shorthand method to create a virtual thread. So you could simply do start virtual threads, and this will start a new virtual thread. Again, simple thing, or same thing as before. There is one more way to create a virtual thread, and that is to use executor service. And now we'll do that right now. We'll create a new executor, which will be executors.new virtual thread per task executor, a big mouthful. So what this method does is it gives us an executor service instance. And that executor service gives us a new virtual thread every time you request it. Because this virtual thread or this executor service is not backed by any thread pool. It doesn't pool threads because virtual threads are not supposed to be pooled. So it gives you a new virtual thread every time you request it. And the way to do that is just call executor.submit and submit a task to it. And in this case, we're going to, again, do the same thing. We're just going to print the current thread. So if I do this, and if I run it once again, I will see a new virtual thread being created. Okay, again, nothing complicated. And with this, I can actually create a bunch of virtual threads. So I can just repeat this a few more times and create a few more virtual threads. And the fact is that because I'm using try with resources, it ensures that all these virtual threads are finished before I exit the try block. So I now see a bunch of virtual threads here. And if you look at their IDs, they are all unique. That means they are all different virtual threads. But they are not using all different platform threads. If you look here, They are all using the same platform thread. In fact, they're using the same carrier thread. So what is happening here? First, this virtual thread was mounted onto this platform thread. And when it was done, a new virtual thread got mounted onto the same platform thread. So basically, the mounting and unmounting that we talked about earlier, we see that in action here. So threads are getting mounted onto the platform threads, and they're getting unmounted as well. So how does this work? How does this happen? How does a virtual thread get mounted onto a platform thread, and how does it get unmounted? What is it actually making this happen? And also, because this mounting and unmounting is playing a big part in the high scalability of virtual threads, what is it actually that is giving this high scalability to these virtual threads? And the answer to those questions is continuations. So continuations is actually the thing that is driving all of this, and we will see that in the second part. So we have finished the first part of the introduction of virtual threads. Now in the second part, we will take a deeper look at continuations. Starting with, what is a continuation? So a continuation can be viewed as a representation of the current state of the program. So your program could be as simple as a sequence of instructions, or it could be a bit more complicated, a bit more sophisticated program with nested method calls or nested loops. But in all these scenarios, in all these programs, you can take a continuation at any point in time in your program. And that continuation object would represent the current state of the program, including the nested method call that you made, including the iteration of the loop that you were at when you took the continuation. And so when you take a continuation, your program is paused there. You get a handle to this continuation object, and you can pass this object anywhere in your program, and then you can decide to resume the program from there, and it will resume from there, and it will go until its completion. So you can also view this continuation object as the rest of the program or the rest of the computation. So your continuation can be viewed as a representation of the current state of the program, because it represents the entire thing of the current state of your program, but it can also be the rest of the program or the rest of the computation. Okay, what can it be used for? It is useful to pause an execution of the program and resume it later. So we can use continuation to pause the program and resume it later. We will see that in action when we explore the continuations API in Java. But before that, I want to highlight something and highlight the fact that the continuation API in Java right now is only used internally, and it is only used to implement virtual threads. So it is not supposed to be used by application developers directly. Well, if this is the case, then you might ask, why are we discussing it? Why are we even learning about it? Well, 3 reasons. One is that knowing about continuations API would give us good insights in the behavior of virtual threads. Secondly, it will help us to understand how the mounting and unmounting is happening. Basically, it would help us understand how our virtual threads getting this high scalability benefit. And thirdly, and more importantly, because it is fun. At least I think it is fun, and we'll see if it is actually fun. With this. So we'll actually explore the continuations API in Java. Again, I will head over to Eclipse and open a new file. And I actually want to create a continuation object. So I'm going to create new continuation. And let's say I get this continuation from a method. So let's say I have a method called continuation. And this method getContinuation returns an object which is a continuation. But hang on, I just said continuation is an internal API, but I'm just using it just like that. How am I able to do that? Well, it is because I have asked the compiler to expose everything in the java.base module. And this is not good. So if you have this argument for your program, it is an indication that this program is not supposed to run in production. So don't do this for your production running applications. I'm only doing it because we want to explore continuations API, and we'll only limit it to that. So for now, it is okay. So with that said, we are now able to use continuation API. So let me do that. And how do you create a new continuation? We can simply do a new continuation. What does this continuation require? Well, it requires continuation scope and runnable. So what is this continuation scope? Well, let's create one. New continuation scope. And this continuation scope, for the purpose of this talk, we can view this as a namespace for your continuation. And it requires a string. The string could be anything. It could even be empty, but let's call it demo for now. And let's use this scope in this continuation, and this requires runnable, right? So let's add that runnable here. And let's say in this case, I just want to print few things. I just want to print A, and then print B and print C. So that's all I want to do, and then just return the continuation here. And now we have our continuation from this method. What can we do with it? Well, we can run it. Okay, so let's run this and see what happens. We see ABC being printed. So what has happened here is basically we get a new continuation, we run it, and it simply runs the runnable. Nothing fancy going on here. But because this runnable is wrapped in a continuation object, we get certain power. And the power is to pause the execution of this runnable. And the way to do that is I can just do continuation dot yield and then pass the scope here. And this will actually pause the execution of the runnable. But I want to do that at two places. So I'm calling yield here and here. So let's see now what happens if I run this program. It only prints A. So what happened here? When I run the continuation, it ran the runnable. It only printed this A. Then it goes here and encounters the yield. And when there is yield, it pauses the execution there. It does not go ahead with the runnable. But it transfers the control all the way to this continuation.run, in fact, immediately after it. And because the control is here, I can do something here. Do something. And it will do that thing. So it prints A, then it transfers the control immediately after continuation.run, and I can do something there. But the continuation is paused. The continuation is paused here. How can I continue the continuation further? Well, I can call continuation.run once again. And if I do that, it takes me back in the continuation, in the runnable, at the point where it was paused, and it continues from there. So it basically then runs this statement, it prints B, then it encounters yield once again, so it pauses there. And the control, again, comes back to here immediately after continuation.run, and I can run once again so that it can continue further. Let's say I don't do anything when I just run, so then it will print C. So basically, it went here, it did this printing, and now the continuation is finished. But what if I do run once again? What happens then? Now the continuation is finished. Let's see what happens then. Well, it throws an exception. It says the continuation is finished, so you cannot go any further. You shall not pass, so I will remove this line, and then I will only execute until the continuation is finished. Okay, so this is how you can use continuation to pause and resume a runnable. And before I move on, I want to highlight a couple of things. One is that this continuation.yield call, it is happening from this runnable, but it does not have to happen from this runnable. So you can have this in nested method calls. So you could have a method call from here, and you could have another method call from there, and another method call from there, and you could have continuation.yield nested somewhere in these method calls. What would happen then? It would pause the execution there, and it would transfer control all the way back to the point where you did continuation.run. And second thing to notice is that this continuation.run does not have to happen from the method of this body. You get a continuation object, and then you can pass that object anywhere in your program. And then you can decide to resume the continuation somewhere later, somewhere far away. That's also possible. Okay, so we see how we can pause and resume runnable. We also see this control is getting transferred. It is a bit abrupt. So how is this control transfer happening? What is it that is enabling this? Well, it is mainly happening with the manipulation of call stack, and we'll see that how that happens with another example. So continuations in Java. Let's explore what happens in continuation.yield call. And for that, we'll take a totally different example. We have this main method, which calls method A. And what happens in method A is it creates a continuation object, creates a new continuation. And if you look at the runnable, we are just executing B, so another method B. But what this method A does is it creates continuation object and it does continuation.run. Then in method B, you call method C, and in method C, you call continuation.yield. So now when you execute main, it will execute A, it will come at continuation.run, it will start the continuation, execute B, come to C, and then you encounter continuation.yield, right? So that is the point where the execution has to pause. And here the control should transfer to method A because that's the one that did continuation.run. Yeah? Okay, so now let's see how that happens. And for that, we have to look at stack memory. And in this case, our stack is getting filled from bottom. So it's getting from bottom to top. And we also have to look at heap memory. So let's say what happens when we call this main method. It creates a new frame on the stack for main. And main method calls method A. This method A creates a new continuation object on the heap, and then it calls continuation.run on it, which then calls method B, which calls C, and C calls continuation.yield. Okay, this is nothing fancy is happening until now. Everything is smooth, everything is what we can understand. But now this is the point where the control should get transferred to method A. How does that happen? Well, that happens by actually moving the stack frames from continuation.yield until B, moving these stack frames from stack to heap. In fact, moving them to the continuation object and then saving it there. And what happens on the stack? On the stack, this top method, continuation.run, it returns. It returns to method A. And now, if you look at stack, you have effectively transferred your control to method A. So that's how the control transfer is achieved in continuation.yield call. Okay, now we understand that. What happens in continuation.run? How does it resume? Again, the same example, but it is extended a little bit with a method for D. We have our A method, B, and C method. And in D, we do continuation.run. So basically, we want to resume. And it is the same continuation object that we had in method A. Now, how does the resume functionality happen? So when do you continuation.run in method D? It should transfer the control to method where it was paused, right? So method C at the continuation.yield point, and then it should resume from there. So how does that happen? Let's look at the stack again. Also look at heap again. Now in this case, on the heap, you already have the continuation object with the stack frame saved in it. And on the stack, you have our main method, which calls method D. Okay, so this method D calls continuation.run. Again, so far so good, everything is fine. But this is the point where the control should get transferred to the point where it was paused, right? So how does that happen? Well, the stack frames which were saved in the continuation object, they are moved back to the stack. And the top stack method, which is continuation.yield, that returns to method C. So this way, you basically effectively transfer the control to the last yield point, and then you resume from there. So that's how the control transfer is achieved. So this control transfer is pretty wacky. What is it useful now for? What is it good for? Well, many things, including these 4 things. So you can use continuations to implement virtual threads and green threads. If you want your own version of coroutines or exception handling, you can do that with the help of continuations. Also, you can have your own version of generators. Now, typically, when I do this talk, I have a longer version of this talk where I have a lot of time, and then I go through 2 of these examples where I implement generators using continuations, and I implement virtual threads using continuations. But this time, because it is a shorter version, I'm going to only implement the virtual thread. So I'm going to show the use of continuations in virtual threads. But if you're interested in generators, you can catch me later, and I can show you the implementation as well. So let's move on to the third part of this talk, where we are going to use the understanding of continuations that we discussed in the second part, and we will create our own version of a very simple virtual thread. Okay, now, when we create our virtual thread implementation, for us to call it a virtual thread, it has to behave like a virtual thread, right? So it has to have certain characteristics. We call them the goals of our exercise. And the first goal is a virtual thread instance. So when we have a virtual thread class created, the instance of that class should not use CPU or platform thread when it is waiting or when it is blocked. Sounds reasonable, right? For a virtual thread, this has to be there. Also, a virtual thread can get mounted on several platform threads during its lifetime, and a platform thread can support several virtual threads during its lifetime. So this is the many-to-many relationship between virtual threads and platform threads. Again, for our implementation of virtual thread, it also has to satisfy this, because these look like pretty reasonable expectations from our virtual thread implementation. Okay, how are we going to do that? We will start with a virtual thread class first. So we'll implement a virtual thread class. Then we will implement a consumer, which will basically use the virtual thread. It will create a bunch of virtual threads, and will also have some blocking calls. And we will implement a virtual thread scheduler, which will have a bunch of virtual threads in it and a bunch of platform threads, and it will schedule these virtual threads onto these platform threads. So this is exactly how we are going to implement this. And this look like pretty logical design. So let's get started with the implementation. And for that, again, I'm going to move to Eclipse. And let me create first our class called VirtualThread. And a virtual thread, in its most simple form, is nothing but a continuation. Actually, a thread requires continuation and a scheduler, but if you externalize the continuation, the scheduler part, so if you move the scheduler out of the thread, then you are only left with continuation. So we're going to add continuation here. Continuation, and let me import that. Continuation called continuation, and continuation requires continuation scope, right? We saw that earlier. So private continuation scope. Yeah, I'm going to actually make it public static final continuation scope, because we're going to need only one version of it called scope. And let me initialize it already here. And again, the string, it could be anything. Let's call it virtual thread. Okay, so we have continuation, and now I'm going to create a constructor for this, public virtual thread. And in the constructor, I simply initialize the continuation, new continuation by passing the scope, and it requires runnable, right? Now let's say the runnable that we require here, we get that as an input to the constructor. Runnable, and then we can simply pass it here. There you go. Okay. And now we want our virtual thread. We also want to be able to run this thread, right? So let's add a method, public void run. And here we're simply going to run the continuation. But before we run it, we'll also print some information. We'll say that this virtual thread is running on, and then we will say which platform thread it is running on. So when it runs, we know which platform thread it is running on, and that's it. Our virtual thread implementation is there. This is all it is needed. This is sufficient to have all the criteria that we said met. But in order for it to be more useful, I'm going to add one more thing, which will be the ID of the virtual thread. And to set the ID, I'm going to use a private static. Should have stopped these meetings. Private static final atomic integer. Oh, something is using my video. I'm going to close this. Atomic integer called counter. This will be new atomic integer starting with a value of 1. So let's say our IDs of the virtual threads are getting set from the value 1. And now let's set that here. So ID will be counter dot get an increment. And that's it. Oh, we also use the ID here, so we know which virtual thread we are talking about. So now we have our virtual thread with an ID. So we know what ID it is and what platform thread it is running on. So we have a very simple implementation of our own version of a virtual thread. Now we want to use this in some examples. So I'm going to create a new class called demo. And this demo is going to have a main method And here I'm going to create a bunch of virtual threads. So let's say VT1 is a new virtual thread, our own virtual thread. And this will, let's say it will print few things. It will print 1.1, 1.2, 3, and 4. We can see these as, let's say, the instructions that our virtual thread is going to execute. And then we will have a virtual thread called VT2, which will do the same thing, but it has 4 instructions, which starting with number 2. Pretty simple things. Okay, so we have our virtual thread class created. We have our virtual instances. So we are creating some bunch of virtual threads, but we want our virtual thread scheduler, right? So let's write the virtual thread scheduler here. Virtual thread scheduler. And if you look at this picture here, the virtual thread scheduler has a bunch of virtual threads and a bunch of platform threads. And it is going to schedule these virtual threads onto these platform threads in a first in, first out manner. Now, I have a question. When we say first in, first out, what is the data structure that comes to your mind? Exactly, queue. So we're going to have a queue of virtual threads. That would be pretty handy to have. Private queue of virtual threads called queue. And this will be a concurrent linked queue of virtual threads. And then for these platform threads, I'm just going to use an executor service. So we'll have a private executor service called, let's say, executor. And this will be an executors dot new fixed thread pool. So it's a fixed thread pool of, let's say, 3 platform threads. Okay, so we have our queue, we have our executor. We want to be able to start the scheduler, right? Only when it can execute these virtual threads. So let's add a method called public void start. And what this method is going to do is it is going to run forever. And it is going to look at the queue and see if there is something. Queue dot is empty. So if the queue is not empty, if there is something in the queue, it is going to pick the thing up from the queue, and then it is going to submit it to the executor. So basically, it is just saying that run this virtual thread that I found in this queue. And it's going to do that over and over again. So that's what the scheduler is going to do. This ensures that you have the virtual threads being executed in a first in, first out manner. Now, we need a mechanism to add some things to this queue, right? So let's create a method, public void schedule, and pass a virtual thread to it. Oops, not this thing. Virtual thread to it, called virtual thread. And we simply add it to the queue here. There we go. So our scheduler is ready. We are able to add some threads to it, and the scheduler is going to pick them up and run them. Okay, now we are able to run our virtual threads here. So let's create a scheduler here, public static final virtual thread scheduler called scheduler. And this will be new virtual thread scheduler. And then let's run this in its own thread. Let's have a new thread created, which will do scheduler scheduler start, toString start, and it will simply start the thread. Okay, so we have our scheduler running in its own thread, and now we are able to add these virtual threads to our scheduler. So I'm going to do scheduler dot schedule VT1 and VT2. So this way we have both these virtual threads submitted to the scheduler, and they will start. So now what will happen if I run this? This will basically create these 2 virtual threads, and we have 3 platform threads here. So it is just gonna execute these 2 virtual threads on 2 of these platform threads, and they will just run parallelly, right? I think that's what will happen. So let's run this and see if that is exactly what happens here. Yeah, so we see that virtual thread 2 is running on a platform thread 2, and virtual thread 1 is running on platform thread 1. And then they both run parallelly in their own threads. Now, if we want to execute them sequentially, like we don't want them to run parallel, but we want to run them one after the other, a pretty straightforward way would be to just simply change this number of threads to 1. And this will ensure, because there is going to be only one platform thread, that they will run sequentially. Okay, let's run this once again and see that if that is what happens. And indeed it does. So virtual thread 1 is running on platform thread 1. It's run to its completion, and then we have virtual thread 2 running on the same platform thread because there is only one platform thread, and then it runs to its completion. Okay, so everything is working fine now, and this is the time to introduce our blocking call because we want our virtual thread to execute some blocking calls, and then we see that it yields the platform thread. So platform thread is open for some other virtual thread to execute. How do we do that? Oops, sorry, I think I opened the wrong demo. So we want to introduce some blocking calls here. And when OpenJDK team, when they implemented virtual threads, they also made the entire OpenJDK aware of this new implementation of virtual thread. So what they did was they went in the entire JDK, all those places where there were blocking calls happening, and they made those places aware of virtual threads so that virtual threads gives up the platform thread, and basically it is available for some other virtual thread to use it. But we don't have enough time to change the entire JDK for our version of virtual thread. So what are we going to do? We're going to create a small simulation of a blocking call, and which will be aware of our own implementation of virtual thread. But before we get there, I want to actually add one more feature, and that feature is going to be thread.currentThread. So what this does is it gives us access or gives us a handle to the currently executing platform thread. Now I want the same thing, but for a virtual thread. So I want to have access to the currently executing virtual thread. And there are actually better ways of implementing, but I'm just going to use a static method here, static field here, public static virtual thread called current virtual thread. Okay, now I have a question. So this current virtual thread, this would be different for each platform thread, right? Because each platform thread would be executing its own virtual thread. So my question is, what do we use? What API we use when we want a variable to have different values for different platform threads? Yeah? Thread local, exactly. So we can use thread local here, and we will do that. So thread local, and because that way we have a virtual thread for each platform thread, and this would work perfectly fine. But I have another question. Do you know in Project Loom there is an API which is a better alternative to thread locals? Scoped values, exactly. So I'm going to actually use scope value here. And then set this. I can also make this final. And then initialize this with scope value dot new instance. And then all we have to do is we have to ensure that this variable is set to the right virtual thread when we are executing our virtual thread, and that place would be here. So I'm going to replace this with scoped value dot dot where this, okay, that's a lot of big change. Okay, so we set this to our virtual thread, and then we run the virtual thread. So what this does is, before we run the virtual thread, we ensure that the current virtual thread is set to the right virtual thread. So this way we have access to the right virtual thread. Okay, so now that we have added this feature, let's go ahead and write our simulation of this blocking call. And I'm going to call that class waiting operation. Because it is indeed a waiting operation if it is a blocking call. So I'm going to add a method here, public static void perform, and it's going to take two things, name and duration. How much time we have? We still have 2 minutes. Uh-oh, That's it's not a lot of time. Okay, let's see if we can get this thing done faster. So or yeah. So when you're executing waiting operation, we want our execution to pause, right? So we simply want continuation dot yield, and we're gonna pass the virtual thread dot scope, and then we actually want to use a timer here. So timer is nothing but a new timer, and in the timer, I'm just gonna set the schedule to new timer scope. Okay. Come on. When a thing goes wrong, everything goes wrong. But yeah, okay. Um, yeah, so this way I'm able to set duration dot, oh yeah, duration into 1000, and then I can just cancel the timer here. And then I want actually the virtual thread, which is currently executing here, which would be virtual thread scheduler dot current virtual thread dot get, and then I'm gonna schedule it onto the scheduler here. So that would be VT, and then I'm just gonna use it here, which would be, let's say, waiting operation dot perform, and let's say I want to do some network call here for 2 seconds, and I want to do, let's say, a database call of 5 seconds. And now let's run this. And in the waiting operation, let me add a system out saying waiting. Okay, now let's run our demo and let's see what happens. So what is happening here is we see virtual thread 2 running on platform thread 2, virtual thread 1 running on platform thread 1, and there is 2 instructions being executed, and then we have some waiting, and after waiting, we see new threads being introduced. So virtual thread 1, which was executing on platform thread 1, after waiting, is now executing on platform thread 3. So it has moved from one thread to the other thread. Also, let me run it once again, because I want to see that it is also applicable for a thread 2. So for example, here, virtual thread 2 was running on platform thread 2. After the waiting, it is running on platform thread 1. So it's basically switched from, or we see virtual thread 2, or virtual thread 1, which was running platform thread 1, which was running virtual thread 1. Now after the waiting, it is running virtual thread 2. So basically that minute-to-minute relationship between virtual threads and platform threads, you can see that in here. I actually had one more part of this demo, but I'm not going to show that because the time. By the way, I started also a bit late. Sorry, Eva. So what I'm going to do here is, yeah, just wanted to mention that I had a demo where we compare the platform thread with virtual threads, and we see that for executing, let's say, 2,000 virtual threads of this version that we created, it finishes in 5 seconds with this virtual thread, and with platform threads, it takes forever, like 15 minutes. So we will we'll skip that demo, but I just want to quickly come back to the source code, the presentation, and then share that you can get the source code over here, and also you can reach out to me for the things that we didn't do in this in this presentation, namely the generator implementation and also the comparison of virtual threads and platform threads. So before I move out of this stage, I just want to quickly summarize what we did. So we looked at what virtual threads are. We also looked at what continuations are. And we used our understanding of continuations to create a simple version of virtual thread. Now with this, we got really good insights in the behavior of virtual threads. We also saw how mounting and unmounting happens. And basically, we got the understanding of what is it that is driving this high scalability benefit of virtual threads. And I hope it was fun for you. Thank you.